I'll probably get started. I'm gonna share the notebook with you guys so you guys can run the code while I'm talking if you want. Just paste it in the chat. Basically, this is a Google Colab and it allows you to run Jupyter notebooks. It's very convenient. Okay, today I plan to go over Pytorch basics. So I'll introduce Pytorch, and then we'll go over the code for an MNIST model. So just handwritten digits recognition. This is an example I talked about last time. Okay. So first, Pytorch. We're gonna import Torch. So that's the package. And then tensors. So at its core, Pytorch is just a library for processing tensors. A tensor can be a number vector matrix or any n-dimensional array. So it's nothing more than say T1 is equal to torch.tensor 4. And the dot here just specifies it's 4.0. It's a floating point number. If you test T1 a data type, a D type, it's float 32. So that makes sense. Then you have a vector. So that's T2 is torch.tensor, and you just put in a list here. And when I put a period here, the whole list becomes the whole tensor becomes the same data type. So these are all 1, 2, 3, 4. These are all floating point numbers. Matrix, and you have 3-dimensional array and whatnot. Then you have tensors can have any number of dimensions and different lengths along each dimension. So for example, T1, all these shapes. This is the shape of 4. I mean the size of 4. This is the size of 3 times 2. There's 6 elements here. And for scalar values or just numbers, there's actually no size for that. And you can't have like different number of elements in each row, but you can have obviously different lengths along each dimension. So that's that. Next is tensor operations. So if we say x is equal to 3, w is equal to 4, and b is equal to 5, and then notice I'll put 2 more parameters here saying requires grad is equal to true. Let's see what that does in a sec. If I do y equals w times x plus b, so this is similar to what I talked about last time. W is the weights times the x, which is the input, and then plus b, which is the bias. So it's 3 times 4 plus 5, which is 17. And what makes Pytorch powerful is that I can automatically compute this derivative with respect to the tensors that have requires grad is true. Remember, w and b, those are the weights and biases, and I have requires grad is equal to true there. So if I go ahead and just say y dot backward, and then I can print out the derivatives with respect to those tensors. So dy dx is none. I didn't actually specify requires grad over there because x is just the input. dy dw is 3 because obviously because w is because x is 3. So when you change w by any amount, it's going to shift by 3. And b is obviously 1 because it's just a constant. So tensor functions. Just really quickly, there's a bunch of tensor functions such as torch.full, and you have a fixed value for every element. Torch.catenate, so you catenate two tensors with similar shapes. Torch.sign. And then here's an important one, which is torch.reshape. Tensor.reshape. You have a tensor T9, which is reshaped into a new arrangement. There's a new shape. And then more in the docs, obviously. Last point on Pytorch, there's it works very well with NumPy because I think originally it was designed to be a replacement for, not a replacement, it was designed to be like NumPy, but you can use with GPUs and calculate derivatives. So you have a NumPy array, and the reason why you want to do this, why it's important, is because NumPy is basically used for it's basically supported by like pandas, matplotlib, OpenCV. So it's supported by lots of stuff, and it just allows you to. It's powerful when you can use it. All you need to do is torch from NumPy, and whatnot, and then the data types, you notice that type float 64, Torch float 64, similar data types, but one is under Torch, obviously. And then you convert it back simply by saying y.numpy. This is important because most data sets you'll work with will be read and pre-processed as NumPy arrays, whether that be images or something, you know. And why do we need Pytorch since NumPy already provides these things and has so much support? Well, autograd, which is computing the gradients, and GPU support. When you're working with like large models, you want to use the GPU. Okay, now we're on to MNIST image classification, having covered all of the basics of Pytorch. So we're going to use the MNIST handwritten digits database. There's 28 by 28 grayscale images of handwritten 0 to 9 digits. We talked about this last time. So here you can see example images. And we'll import Torch Vision and because it has utilities for working with image data, and Torch Vision also gives you these popular data sets such as MNIST or Fashion MNIST or whatnot. And you can import popular data sets automatically using this library. So I'll just say data set is equal to MNIST, which I just imported. The root is in the data folder. Download is equal to true because I want to download. When that downloads, we'll move on to the next. It's still downloading, but when I say length of the data set, you'll get 60,000 because there's 60,000 images that we use to train the model. There's also 10,000 images used to test the model. So if you guys remember me talking about how, hey, there's a test data set and there's a train data set. The test data set is solely for testing how well it does. When you're training it, you will never see the test data set. It's just for evaluation, right? So that's why you would have that's why you have two data sets. And you can download the test data set by specifying train is equal to false, which is default true, obviously. And the length of this would be 10,000. So I'm still waiting for this to install. I'm gonna keep explaining for now, because the outputs are here from a previous time that we ran them. If I were to sample an element from the data set, like data set, the first element, the first item you would see is pil.image. So this is a imaging library pillow, and it's an image, right? So we can view this image within Jupyter using something called matplotlib. And it's just a graphing library. So I'll import matplotlib as plt. And then I'll use a magic command. So this thing with the %sign. You'll see this in Jupyter notebooks, and what all it means is it's configuring the Jupyter behavior. It's not actually Python code or anything. Okay. If I say image, comma label is data set, so I'm just splitting this into two things: the image and the label. When I say pl.im show the image, you'll see it shows the image. So this is a 5, and I print the label, which is 5. By the way, inline is just saying, hey, I want to show this inline in the actual Jupyter notebook itself. I don't want to pop up a new window. So this is what one item from the data set looks like, right? There's an image and there's a corresponding label to it. And the problem right now is that Pytorch doesn't know how to work with images. These are just, if you remember, these are PIL images. Now, the solution would be to convert them to tensors by specifying a transform while creating our data set. So we're creating a data set, and Pytorch data sets allow us to specify a transformation function. So what we're going to do is we're going to use this transformation function to transform the image to tensor. So something called toTensor here, right? So go ahead and run this. Okay. So I'll use the toTensor to convert these images into tensors that I can use for my model, right? Here. Now I say import Torch Vision.transforms as transforms. And then I'll say, so this is the same thing we just did, there's nothing new. MNIST data set, the root is data, train is true, and transforms. Now I specify transform is transforms.toTensors. So now instead of returning all those pillow images, I'm going to get tensors. So now you can see I can split it into two things now. I can say image tensor and label is equal to data set 0. And I print this, and I'll get a torch.size 1 by 28 by 28. And then the label is 5. Now compare this with what we just did, which was image label. So I got a pillow image, I plotted it, and then I had label of 5. But now, because I specify transfer.toTensor, I can do that. 1 by 28 by 28, because obviously there's 28 by 28 pixels, and there's one image right now. And if I actually print out the maximum of this image tensor and the minimum image tensor, you'll see that these are values ranging from 0 to 1. That's what it is. So tensor 1 is the max, and tensor 0 is the min. And when I print out just a portion of this image, a portion of this tensor, what you'll get is these numbers. And again, just reinforces that these are values between 0 and 1, and this image has been represented as a tensor. Now, if I want to plot this, I can still plot this. And I just use, so this image right here is this section plotting. These are just the subsection of 5 by 5 pixels, right? You can see that zeros are dark, and over here 0.9922 is a light value. Okay. So quick recap. I've gotten my, okay, now they've run. Okay, cool. Quick recap. I have my MNIST data set here. With it's in the data folder, and this is the training data set. And when I got this data, I transformed it to tensors, right? So now when I look at, say, data set, the first element in here, I'll get an image tensor and I'll get a label, which is a 1 by 28 by 28, just for the 28 by 28 pixels with label of 5. So cool. Let's move on to talking about validation data sets. So we talked about the training set and the test set. The test set is to compare different models, or like to report the model's final accuracy, right? You don't want to ever see the test set. Well, the training set is used to train the model and to compute the loss and to adjust these weights using gradient descent. Now we have something called a validation set. This is used to evaluate the model during training to adjust hyperparameters, such as learning rate or, such as learning rate. And then I want to pick the best version of the model. The reason we want to separate this from the training set is, again, if we pick the best version of the model and we only had a training set, then what we're actually doing is we're picking the best version that does, we're picking the version that does best on the training set, right? So it's going to start learning. It's going to start being biased to this training set. When I separate a validation set, so it's almost the same thing as a test set to help us pick models, except it's not a test set because we want to leave the test set for the final accuracy test, right? So what we do is we take the 60,000 and we can just split it up into 50,000 and 10,000. So I'll have a 50,000 for training, 10,000 for validation, 10,000 for test. And we can use this using random split method from Pytorch, right? So from torch.utils.data, and you can always check on the documentation and look back on this notebook if you guys want to review. We'll have a training data set here and a validation data set here. By splitting this data set, remember this data set is, scroll up, this data set is just a bunch of image tensors and labels. This is one element of the data set. So over here, I split it into 50,000 and 10,000. And then now if I check the length of the training data set and the length of the validation data set, I have I have 50,000 and 10,000. The next move is to load the data in batches. So when we're training, we want to train in batches. So it's not, so it learns after each batch. The reason we want to do this is because if you think back into our last meeting, when I talked about it's adjusting the weights, right? We don't want to adjust the weights after all the training examples in the trainings data set. We've gone through all of them. We don't want to do that because it'll be too slow. And our progress, we only get a progress update every full epoch, right? But when we go by batches, we go by one batch at a time, and we're using 128 images right now. And we can use something called a data loader So here's a train loader. All we need to do is data loader. We use a training data set, and the batch size is 128. And same thing for the validation loader. You notice that I say shuffle is true because the batch in each on all the epochs should be different when it comes to the training data set. Cool. Now we're moving on to the model. Okay, we talked about a linear regression model, and now we can do a logistic regression model. So basically, this is just categorizing something into several categories. And in this case, it would be 10 categories for each digit. Same thing as before, we're using the weight time, we're using x times transpose of w. So it's just weight times the input plus the bias. That's all you need to keep in mind. And Pytorch actually has something called nn.linear. So we can create the model instead of manually creating these matrices. And we want to flatten the 1 by 20 by 28 into 784 before passing it into the model. And finally, the output for each image of this model will be a size of 10, and each element is signifying the probability of each particular target label. So the first probability would be the probability that that handwritten digit is a 0. W times, it's actually W transpose, times X plus B. And then our forward pass, remember we're passing forward propagation, we're passing through the inputs to the outputs. We just say XB, so it's the input batch, and then we reshape, X, and then we're reshaping X into, we're using -1 because it's a batch, we don't know, we want to retain that. Keep this the same, and the 784 is the 28 times 28. So we're just flattening these 784. The output will be self.linear, so just passing through, putting it through the linear instance here, and we just return the output. So model equals eminence model. Now what we can say is for images labels in the train loader, this is where the loaders come into play. We have our data set. But now we're putting the data set into a loader. The loader gives us images and labels for each batch, right? In this example, we'll say, we'll print the images.shape and we'll print the outputs. So here's the example. It's 128 by 1 by 28 by 28. So it's 128 because there's 128 images in this batch. It's 1 by 28 by 28 because for each of those images, if you remember our first element, this is what it looks like. Our output shape will be 128 by 10, obviously, because there's 128 images, and for each of those we have 10 numbers, which are supposed to represent the probability, but they don't yet. If you notice right now, you have negative 0.2712, negative, positive. So these aren't actually probabilities right now. And if you know what the softmax does, basically it turns these 10 numbers turns these outputs into probabilities, so they can all sum to 1, right? I'll import this from torch.nn.functional, and I'll apply the softmax for each output row. So each of those 128 output rows, I'll apply a softmax, and I'll look at the probabilities. So for example, we look at the first two. Let's see, 0.06, 0.07, and you notice that these things sum to 1. Right now, these are all very low probabilities for each because it's kind of random, right? These are all about 0.1 each. Make up the 1. And if you add all these together, it's obviously 1. So now we have probabilities in place. So how do we determine the predicted label with given these probabilities? Well, that's easy, right? You have your probabilities. All you need to do is just pick the highest probability. And we can use torch.max to do that. We'll choose the max, we'll return both the maximum probability and the index of that maximum probability. And what we care about is that index, so we call it predictions. So here's our predictions, it's 5, 3, 5. And if we look at the actual labels is actually these numbers. And you'll notice that these are obviously completely different. Well, that's because our model just does the linear, has the weight matrices as a random matrix, right? So obviously it will be random and it's not very good. We know it's not very good Yeah, we know it's not very good. And again, I talked about a loss function to talk about how bad is it actually doing. We might think, oh, we want to do accuracy. So of all the examples, how many do I get correct? And for humans, yeah, this makes sense to us. It's doing poorly right now because it's only getting this percentage correct. But we can't use this for the loss function because it's not a differentiable function and it doesn't take into account the actual probabilities predicted by the model. So it doesn't have like feedback for these incremental improvements I talked about. Remember, we're adjusting the weights and biases. For this reason, we'll use something called cross entropy. And you can learn more about this on your own time, but just quickly. Well, to interpret this, you can just interpret this as e to the power of negative loss to have the as the predicted probability of the correct label. This isn't too important right now. Now to the actual training of the model. We want to train the model now that we have our data loaders and whatnot. So here's the pseudocode. For epoch in range, so a single epoch is a single pass through the whole training set, right? We want to go through the training set multiple times, and each time we go through it, it's going to be called an epoch. So in each epoch, now we're dealing with one pass through of the training set. Now our training sets will be broken up into batches, right? We have for batch and train loader. And what we do is we generate our predictions, we calculate our loss, which means how bad are we doing? Then we compute our gradients, which I talked about last time. Now we know how bad are we doing. Let's compute the gradients and let's update the weights, moving in the direction of the negative gradients, right? And then let's reset the gradients so we can do that again for the next batch. We do these for all the batches, and then we go to the validation, which would just let us know how well it's doing right now, right? For batch and val loader, we want to generate the predictions, calculate the loss, and calculate the metrics such as accuracy, right? We're not actually doing any learning here. The learning is happening in the training, using the training set. Over here is just giving us an accuracy for every epoch, right? And then we'll log these things, or we can append these to a history. Array. So this code below is just the pseudocode in actual code. So we define a fit function. Our optimizer, this is just how we're optimizing, and our history, this is keeping track of epoch-wise results. Again, for epoch in range epochs, for batch in train loader. So loss is model.training step. We're gonna define a new model. We haven't actually defined these steps yet, but training step, loss.backwards. And with optimizer, we'll take a step. Remember, all the optimizer is doing is moving in the direction of the negative gradient. And then we're gonna reset these gradients by saying 0 grad. So we can do this again from the batch. And of course, there's a validation, which is evaluate epoch, and for the epoch end, we get these results, and then we just append the results to history. And at the very end, we'll return the history, which is useful for graph accuracy. So, evaluate is nothing more than saying, hey, go through all the things in the validation data set, and then calculate those metrics, accuracy and loss, right? And here's the new MNIST model. Again, the constructor is the same. Forward now is also the same. But we've added a training step, which is given a batch, and given a batch, it's going to split the images and labels, and it's going to pass in the images to itself. It's going to run through, it's going to get an output, right? Return out with self images. Self basically calls forward. And then I'll say, and now I calculate the loss, right? So I generate predictions and I calculate the loss, returning the loss. For validation, it's very similar, except we're also calculating accuracy. Again, accuracy isn't important for training because the computer won't do anything with the accuracy. It's just for humans to understand. Validation epoch end is at the end of each epoch. We basically just compile these losses and combine these accuracies. And we return that. And then we can log it with an epoch end statement. Now we say model is MNIST model. So result 0 is evaluate model val loader. And this is how well it's doing right now. So it's doing terrible right now, right? The accuracy is below 10%. And if I say history is equal to fit, these things, it will run for 5 epochs. And for each epoch, and this is learning rate. If you remember, this is how much we're adjusting in each step. You notice that the accuracy gets better. So it goes from 58% to 72%, 75%. And if I run this, it's going to take a while. We're almost out of time here. So just one last thing. Test for the individual images. I can take our test data set. And then in our test data set, I can extract individual things. And to predict an image, just remember you have to you have to flatten out the image, pass it through our model, and the prediction or the indices of our maximums is what matters. That's a prediction. That's it. It's 1:15, so that's the end of lunch, right?
Yeah, I think, yeah, it ends just now. Should be good.
Right.
Alright, see you guys. Thank you guys for coming. See you guys next week.